Well, hi everyone. Thank you so much for coming to this week's SPAAM seminar. Our first speaker today is Hanna Palya from IGPP, talking about vectorization and clustering of natural language chief complaints for syndromatic surveillance. Go for it, Hanna.
Yeah, almost. Hi, I'm Hanna. Thanks for having me. Yeah, I'm with the Institute for Global Healthcare Planning, which is basically just a thing between the medical school, the business school, and here, and then between the medical school and here. That's why I have a million supervisors. And yeah, I'm going to be talking about syndromic surveillance and basically some playing around that I did with data I had access to. I started this project in the summer, so it's mostly going to be just a list of methods and a bunch of things that didn't work out and maybe some things that worked out. Yes, this is the structure of the talk, because I assume that yeah, syndromic surveillance is not really in your vernacular. And then I'll go through yeah, how it works and where machine learning can fit in. I guess here the definition of machine learning I'm using is like any yeah, any supervised or unsupervised methods that are shallow machine learning. So I'm not going to go into deep learning here because I've just done big machine learning. And I'll go through how I did this with vectorization techniques and clustering techniques. And then I'll show you some results that I had. Yeah, can I have a show of hands if you've used natural language processing methods, just so I know how much I should go into detail? Yes, okay, sorry, I think I will go into some detail. Okay, let's go. So this is what syndromic surveillance looks like. This is what either like a larger regional or a national system would look like. You can find these systems in the UK, in the US, in Taiwan. Not every country has it, and definitely like a fraction of countries that have it actually publish about it. But yeah, so the data comes from GPs or emergency rooms. This is symptoms that people turn up with, and sometimes also preliminary diagnosis or something between just symptom description and diagnosis. And this gets reported to a health security authority. You can also get some extra data sources from social media and search engines. There was like a big boom of this in like 2013 to maybe 2017, and now like basically none of the national systems use them anymore, but some more local ones do. And then these symptoms, again, like with social media and with search engines, these are self-reported symptoms. These symptoms get grouped into syndromes. For example, like cough and a runny nose would be grouped into influenza-like illness, but it could also be grouped into COVID-like illness or upper respiratory tract infection. So yeah, I'll get back to that. And then with the syndromes, they are trying to track outbreaks with real-time aberration detection, and then some systems also try to do a bit of forecasting, mostly pretty short-term, like 1-2 week forecasting. Yes. Basically, I'm also doing a systematic review other than what I'll present here, and doing that, I found that people have used some sort of machine learning for more accurate syndrome definitions, for the actual aberration detection, and also for forecasting. Here, I'm going to talk about syndrome definitions, and to like kind of motivate this a bit, I put out the syndromes that the real-time surveillance team at the UKHSA tracks. You can see that it is a wide range of things, that there are really big categories, really small categories. So at the UKHSA, these so the symptoms get assigned to syndromes basically by if-then rules, and these were defined some time ago, and they don't really change, except you can see that there's a COVID-19-like indicator, which was manually changed, and it took months from the first COVID case in the UK to actually change it. So what I'm trying to do is find ways of assigning symptoms to syndromes that don't require this manuality, and so you can detect novel outbreaks more automatically, or a bit faster. Yeah. My data sources, I mentioned before that I don't have access to the UKHSA data set yet. This is while I was doing this whole project. So I found a synthetic data set with emergency room chip complaints from simulated New York hospital. To, I guess, 2 data sets were there. One simulating a zombie outbreak, another one tuberculosis outbreak. And then I also found another data set that I could have access to, which was real data, which was de-identified. So there's no ground truth outbreak there, and also, like, obviously none of these have real time or spatial components. So the grouping of symptoms is only based on semantics. These are the 2 data sets. This is the real one. You can see that it's a lot messier. There's a bunch of spelling errors. And then there's the simulated one. It's not the zombie one. It's the tuberculosis one. Sorry. Yes. So I use some vectorization methods. These are the basic steps of vectorization. You basically cut up a string in whatever way you like, and you map it out to some high-dimensional vector, which is good, because then you can measure distances in many ways between these concepts. So some vectorization methods, I won't spend too much time on these. Basically, like, as expected, the vector libraries, or the vectorization methods that use vector libraries that were clinical data specific, performed better than the ones that weren't. And then this bioclinical BERT is an early LM, like, it's quite old now, but that's okay. This performed the best on the real data set, because it can deal with the all sorts of different ways of spelling symptoms. Yes, and then my clustering algorithms, I wanted them to cluster things that were similar or co-occurring in symptom definitions to go into the same clusters, and then I wanted ones that were not similar to, that were different, to go to different clusters, and for this difference to be meaningful. This is, again, the most basic one, k-means. Yeah, I think you might have come across it. Yeah, it's the one I used, clustered based on Euclidean distance. Yeah, based on this rule, this is the function that it's trying to minimize. And then K prototypes, very similar, but the good thing with this is that you can also use categorical data together with the numerical data, your vectors. It wasn't very important for my data sets because I didn't have actual spatial data, but it could have been good if I had like different hospitals, or like if in the future I have this. So that's why I want to include it. DBSCAN works a little bit differently from K-means and K-prototypes because it's density-based, but so basically finds, or like it starts with a random point in your data set, sees if you have some threshold of, again, distance of what is, like what's a near point, what's gonna get into N, and then if this is more than what you set as your minimal points in your cluster, then this can become a cluster. If it's lower than that, then it's really going to become a border point to a different cluster or a noise point. And this like noise point is important that yeah, DBSCAN can filter these out. I will show that in a couple of slides. Yes, the last one that I'll talk about is agglomerative. Here you start from all of your data having the like its own cluster, and then here big I cluster them together based on variances, and then you define some cutoff point where you're happy with your number of clusters. And these were my results from the synthetic data set. This is the tuberculosis data set. You can see that K-means was the best in terms of, here the sensitivity and specificity is whether it found the tuberculosis cases in the tuberculosis cluster. So I was focusing on this sort of ran through outbreak. And then the silhouette score is a silhouette score of the tuberculosis cluster. And then the meaningful clusters is just a number that made some sense and had a silhouette score that was more than 0. Yes, you can see K-means performed the best in terms of sensitivity and specificity, but it's good to pay attention to DBSCAN having a lot more meaningful clusters. Yeah, these are the outbreak clusters from the zombie data and from the tuberculosis data. And this is the K-means. These are the K-means clusters. It's all on top of each other. It's quite bad. But there are some clusters that make sense. The tuberculosis cluster was good, which was the one that I started to find. There were other meaningful ones. Cluster 5 was poisonings, but cluster 23 just like had a bunch of unrelated things in it. So not so good in this way. There are like some questions here, like what do you actually want your anomaly detection method to do? Do you want to see everything that's going on, or do you want to see like the most notable things? And then this is with DBSCAN. You can see like lots of things are purple. That is the noise cluster. And please, yes, and then I can remove the noise cluster, and it's much nicer. And every cluster here is meaningful, maybe not important, because traffic accidents are not important for infectious disease detection, but they are meaningful, which is great. But I did remove 80% of the data with this tab. So again, back to that question of what you actually want your method to do. And then this is from the real data set. I've been doing somewhat different things to this data set than the synthetic data set, because I just chose bioclinical BERT as vectorization method from all the preliminary results. And then I chose DBSCAN as a first step in clustering. And then now I'm trying to basically build ensembles. So I run DBSCAN first, and then on the noise data, I run agglomerative clustering to try to find anything that was lost in that noise cluster. But this is, yeah, I like this picture because it shows like the bad stuff and the good stuff. Obviously, you don't want clusters based on like sitting around a normal, and you don't really need the unknown chip complaint cluster either. You can get rid of these up to clustering as well, but yeah. But this one, the cluster 88, I was very happy with it because based on like 1 or 2 chief complaints having both some kind of bite and rabies vaccine, it clustered together everything that was some sort of bite or even their bad exposure, and that was rabies vaccine. And this is the sort of thing you would want your symptom grouping algorithm to do. And then I put up some more of my struggles with the ensembles that I mentioned before. There's like a bunch of metrics here, and you can see that a lot of them trade off against each other. There's like a reasonably good one with the like UMAP to HDB scan. This is, but UMAP is a variation of the dimensionality reduction technique that I used. So there are some that seem better than others, but I think a lot of the future work will involve just deciding which trade-offs I'm willing to take. So these are my next steps. I already talked a bit about the ensembles, and then comparing sort of my chosen clustering method to latent literacy allocation, which is a topic modeling method that has been used for similar symptom sorting work. And then once I get my hands on the real data, then I will try out these clustering methods, and then we'll see whether I will progress with that or go more towards the forecasting route. There's no natural language processing in this real data, but there's still like codes for symptoms that you can look at in a very similar way, just no natural language processing, only the clustering. And yeah, that was it. Yeah, I am taking any questions or suggestions, just comments, anything. Yeah, thanks.